In this lesson, we will be learning about vectors, which is a very useful tool when adding in physics when you need to add together forces or accelerations or anything really that can happen in multiple directions. So this allows us to take what we know about one-dimensional physics and bring it into the three-dimensional world. The first thing we need to learn about is what a vector is. If I ask you a question like 2 plus 2, anybody can tell me, well, most people can tell me, the answer is 4. When we're dealing with this, we're dealing with scalar quantities. A scalar quantity is a quantity that only has a magnitude but no direction. A vector quantity, on the other hand, has both a magnitude and a direction. When looking at the question 2 plus 2, what does it equal as in terms of vectors? The answer really relies on what direction those vectors are in. First, let's look at the simplest case. If I have two vectors that are in the same direction, then when I add those two together, 2 plus 2 indeed does equal 4. So this red vector that I drawn is my resultant. So I have a vector that's 2 units long plus another vector is 2 units long. I get an overall vector that is 4 units long. However, if I have vectors that are in opposite directions, as in the option B here, when I add those two together, if I can grab them, I get my overall vector is nothing. Because in this case, if I go 2 south followed by 2 north, and I put those together, I haven't gone anywhere at all. Option C, if let's say I walk 2 miles north and then 2 miles east, and I wonder, well, how far am I from my starting point? I take my vectors and I line them up properly. And I will find that I have not walked 4 miles, but instead I will have walked 2 miles 2 times the square root of 2 miles, which is less than 4. It's the hypotenuse of this triangle. So you can see 2 plus 2 always equals 4 when you're dealing with scalars, but when you're dealing with vectors, the direction is what matters. The resultant, as I've shown you with the red arrow, is the sum of 2 or more vectors. You always find the resultant by placing all vectors head to tail and then drawing in a vector from the tail of the first to the head of the last. Notice the spelling mistake. So there is a vector addition simulator that we may be using in class. You can take the vectors and you can grab them and put them in any direction you like. And when you're looking at each vector, you can see it tells you different things. What the overall magnitude of the direction of the vector is, what the direction of the vector is, and then these components of the vectors. So how far it's moving in the x direction and how far it's moving in the y direction. What these x and y mean is if I was to put this on the x and y coordinate system, and the rx of 15 means that this goes 15 units over in the x direction, and the ry of 14 means it goes 14 units up in the y direction. If I take this second vector and put it onto the coordinates, you can see that it goes negative 16 in the x and positive 12. If I want to see what these two vectors add up to, they add up to this green line. To see how they add up to this green line, I have to put the vectors head to tail. Right now they're tail to tail. So if I move this vector up and put the tail of one next to the head of the other, then I can move the resultant vector over and I can see how they add up to give me the overall resultant. If I put in a third vector, you can see the overall amount of the resultant vector changes, and as I change the direction of the third vector, the magnitude and the direction of the resultant vector changes. Again, if I move it so it's head to tail, we can see how it adds up to the resultant. So to add vectors, I always need to make sure that I start at the tail, go to head, tail of the next, to the head, tail of the next, and my resultant is always gone from the tail of the first to the head of the last. The next thing I want to talk about is the independence of vector quantities. And boy, I'm just having a hard time spelling vector. That's bothering me. There we go. So, anytime two vectors are perpendicular to each other, they are said to be independent of one another. Whatever happens in one direction cannot affect what happens in a perpendicular direction. You can see here I have an animation of two boats, one going across a pond and one going across a river. The river is right now not flowing. I will start its flow in just a moment. Right now you can see the two boats cross the bodies of water in equal amounts of time because they have the same horizontal component of their velocity. I'm going to start the river flowing as soon as the boats reach again, and you can see that it still takes the same amount of time to cross the river, even though one flows down. So we'll start that again, see if I can get better timing. Okay, so you can see even though one's moving to the side, they still cross in the same amount of time. The speed the boat goes across the body of water has nothing to do with the speed in which it crosses to the side. Again, this is because the two directions are independent of one another. We've already looked at how we can add vectors by drawing them out, but what about just adding them mathematically? When you're trying to add perpendicular vectors, you use some things you've probably learned in math class. Pythagorean's theorem at a squared plus b squared equals c squared, and a trig function tangent, which is the opposite over adjacent. If I want to add these two vectors to know what they are, this one is 7.39 centimeters long, and this one is equal to 14.32 centimeters long. Whoops, that wasn't supposed to be there. I can find the length c by taking the square root of 14.32 squared plus 7.39 squared to get that it's 16.11 centimeters. I can get the angle by taking the inverse tangent of the ratio of the two sides and find that it's 27.3 degrees. I can check this work by taking again, placing my vectors head to tail. So I move the vector over to here, and then I could get a ruler out. So we'll get a ruler. And again, I place it at the tail of one. I'm going to need it a bit longer. Rotate it up. And we can see it is indeed about a little over 16 if I place the ruler correctly. It's a little over 16 centimeters long, and the angle is at, if you look at over here, negative 28 degrees, which is about the 27.3 I predicted by the math. So we've seen now vectors split up mathematically when they're perpendicular to each other. Vectors can also be broken up into their different components. You can do this again by learning what you probably learned in trigonometry in math class. That is, the sine of an angle is equal to the opposite over the hypotenuse, and the cosine of an angle is equal to the adjacent over the hypotenuse. If I have one vector, the red one, at 10 newtons at 30 degrees off the horizontal, I can figure out a horizontal component of that vector by using the cosine formula. And I will find that this adjacent side must equal 8.7 newtons. I can find the opposite side to this 30-degree angle by using the sine formula, and I will find that the side is 5 newtons long. Being able to break a vector into its horizontal and vertical components can be very useful in finding answers to various different problems, as we will be seeing in class. Here's an example problem that comes up in introductory physics a lot. If I have an object that is sliding down a ramp, I want to know how fast it's accelerating. We all know by now that if I drop an object straight down, it will accelerate at 9.8 meters per second squared. However, when going down a ramp, this is not true, especially if the ramp, as in this problem, has friction. Friction will slow down any acceleration. To be able to know the force of friction, I have to know how strong the normal force is. So there are a lot of questions that are going to be answered. Now, in the past, we've always looked at the normal force was equal to the weight. Well, this is only true on a horizontal surface, which we do not have here. So the first thing we need to do, like doing problems with forces before, is we need to make a force diagram. So if I diagram all the forces, I can see there are three forces acting on this object. There's the force of friction acting up the ramp. The force of gravity, as always, is acting straight down. And the normal force is acting perpendicular to the surface, which is what the normal force means. If I can find out what this normal force is, I can find the force of friction. And then the weight is equal to mass times gravity, so I will know all three of these forces, and then I can solve the problem. Looking at how to do this, the first thing I need to do is I need to take my weight and I need to break it up into two different components. One component that's parallel to the ramp, so this is the portion of the weight that's actually pulling the block down, and one part of the weight which is perpendicular to the ramp. If I look at my second law, in the parallel direction to the ramp, I find that the portion of the weight that's parallel to the ramp minus the force of friction is equal to the mass times acceleration of the block parallel to the ramp. In the perpendicular direction, I see that the normal force minus the weight that's in the perpendicular direction is equal to the mass times acceleration in the perpendicular direction. Since the block will not accelerate perpendicular to the ramp, this term is equal to 0. So here, instead of the normal being equal to the weight, I find that the normal is equal to the perpendicular portion of the weight. So I'm going to need to know about the weight to answer this problem. So the first thing I do is I find out what the weight is. It's 10 kilograms times 9.8 meters per second squared, or 98 newtons. The parallel component then is then 98 times the sine of 20, because this parallel portion of the force is the opposite side to this 20-degree angle in this triangle. That equals 33.5 newtons. The perpendicular component of the weight is then the cosine, 98 times the cosine of 20, since this is the adjacent side, or 92.1 newtons. I now know what the parallel portion of the weight and the perpendicular portion of the weight is that I can plug into my formulas. The first thing I need to do is find out what the normal force is, and the force of friction. Since I now know the normal force must be equal to the perpendicular portion of the weight, it is 92.1 newtons. If I plug that into my force of friction formula, I take 0.2 times 92.1 newtons and find that the force of friction is 18.4 newtons. Now, using my other direction, the parallel direction, I can find out my acceleration, because now I know the 33.5 newtons from the parallel portion of the weight minus the 18.4 newtons from the friction is equal to my mass times acceleration. Plugging everything in and solving for A gives me an acceleration of 1.5 meters per second squared. I know this is probably a lot to take in, and I just want to go back and review what we did. First, we drew our force diagrams. Just like what we've done in the past, we want to break up not into a horizontal and vertical direction, but in two other perpendicular directions that are going to be independent of each other that will help us make this problem easier. So the directions we chose are parallel to the ramp and perpendicular to the ramp. Because the weight is neither parallel to the ramp nor perpendicular, we must break it into component vectors in which it is. Then we can see that in the parallel direction we have the parallel portion of the weight and the friction portion. In the perpendicular direction we have the normal force and the perpendicular portion of the weight. We've set those net forces equal to ma in each direction and then plugged in all what we knew and solved. We will be working through many of these problems in class, and hopefully we'll clarify some of the confusion that you may have as we go.